Okay, good morning, everyone. We might get underway with our webinar. Actually, we've got 250 people registered today, which is awesome news. It's probably our biggest registration. Probably a really important topic, which is probably why it's generated a lot of interest. I'm Darren Falconer from Best Farming Systems. We're happy to be hosting Walter here to talk all things nitrogen. This is a series of webinars we're doing now for Best, and this has been our we're up to 5 or 6 now, so be sure to log into our website and have a look at our webinars if you're interested to have a look. But today's topic is very important. I feel that after talking to farmers over the last 12 months at all the field days that we've been at, that nitrogen is a very hot topic, especially with the price of it, the availability. So it'll be good information that we'll be able to find out ways that we can utilise sort of organic nitrogen to help us farm. And here at Best, we've helped a lot of farmers reduce their reliance on synthetic fertilizers by activating biology. So there is a way to help farmers get off that high input system. So we can certainly help. So Jess, I'm going to pass over to you just to talk a bit about the questionnaires and stuff. So I'll pass over to you for the housekeeping.
Thank you, and yeah, good morning, everybody. So just some quick housekeeping. So we are recording the webinar for anyone that needs to jump off, or if you know someone that wants to look at it later, it will be up on the website. We are just going to obviously here to listen to Walter today. We will just leave all the question and answers until the end, and then we'll go through them with Walter. We do ask that you just try and keep it on topic as best you can. But yeah, I think we'll just get straight into it. As always, thank you to Luke for co-hosting with us. It's always good to have you and your knowledge here. So I'll pass on to you, Luke, to say hello, and then we'll get on to Walter.
Thanks for that, Jess. Yeah, so I'd like to thank Best once again, Best Farming Systems once again for hosting this and helping us get this information out there. If it wasn't for companies like Best, these things wouldn't happen. Once again, I'd like to thank Walter for coming along. I rang Walter a month or two ago about doing this particular webinar on nitrogen, and I just thought it was it's been such an important topic for a long time, but it's really come to a head with the way things are at the moment with the pricing and supply. But it just affects so many things. Like it affects firstly the nitrogen cycle. It affects the carbon cycle, the water cycle, the nutrient cycle through overuse and mismanagement. So it's just so important that it's something that we really need to get right. And so Walter's put together, I'm going to say, another fantastic presentation on all of these things. And so we'll pass you across to Walter and yeah, we'll have a listen. And then, yeah, if you could once again just put your questions in the Q&A box so we can follow along. Anyway, there you go, Walter. We'll leave it to you.
Okay. Thank you very much, Luke, and good morning, everybody. And I'm impressed, 250 people registering, but fully agree with Darren, with Luke, with Jess, the importance of nitrogen. But let's get into the details actually more than we normally do. We normally just look at nitrogen as another mineral or another fertilizer input. And as with fertilizer, we just assume, yes, we need nitrogen, but really we don't go into the inside and understand how it works. And so today I'd like to really explore that a little bit more. What is a role that nitrogen plays in nature, and how does that nitrogen cycle in nature function, and what do we need to learn from that? The second part, we want to then look at, well, what have we done in industrial agriculture, particularly the last 100 years, basically to change that nitrogen cycle through basically fertilizer, and what impact is it having? And really, where does that understanding now levers going into the future, because the future has to be sustainability, resilience of land systems, these natural systems, much more so to give us the long-term resilience and productivity of our cropping systems. And then from that, going into the question of, okay, how can we, by improving soil health and biology, by biostimulating these natural processes, significantly reduce the need for fertilizer, nitrogen fertilizer addition? Because nitrogen is always going to be essential for growing things, but how much of that growth can we drive through these natural regenerated processes rather than being dependent on fertilizer additions? And then at the end, I'd like to go back to some of the big picture sort of issues, because how do we actually, at a industry level, global level, look at changing our nitrogen economy, the whole ecology, and basically securing food futures profitably without the degradation and destructions that would be otherwise occurring? Because obviously nitrogen, while it's essential for growth, is also very, very dangerous material if it's in excess, because it's one of the key drivers of degradation of the soil. But we'll come back to that in details. So look, they're the key issues that I wanted to focus on in this talk. I want to talk about for 45 minutes or so, and then we'll basically open it up for questions. Very happy to, of course, answer any questions. The knowledge is all there, the science is all there, but obviously tailoring, applying it to your local circumstance, that often needs, you know, specific local knowledge, observation. So bear with us, we'll do the best we can, but most importantly, it's actually making the point that, yeah, you need to sit down with your agronomist, analyze things locally, and then look at what are the pathways that we can actually help restore these soils, this nitrogen economy at that local level. But look, starting off, we're all in the business of agriculture, and of course, agriculture is all about growing plants. And, you know, at the very basic level, it's just beautiful, wonderful. It's simply a matter of harvesting sunshine, harvesting CO2, using some water, and of course, through photosynthesis, producing sugars, right? And really, that's what plants do. It's what drives the whole food system of life on this terrestrial planet, certainly above ground. I mean, 99.9% of it. And really, it's that photosynthesis, the production of sugars from the CO2 in the air that's really the basis of life. And we always say, look, yep, there's photosynthesis, and that's what we as farmers do. But we tend to forget that, yep, this is also a biochemical process. So what makes that photosynthesis work? And of course, the process of plant growth very much involves then enzymes, basically changing, the water, the CO2, absorbing the solar energy, making the sugars. And those enzymes, of course, are made up of chains of amino acids, proteins effectively. And all of these proteins, of course, are basically nitrogen. So whereas carbon is the structure through which we actually build crops and sugars and the building block of plants and life, in a sense, nitrogen is a natural biochemical engine of that growth. Okay, so there's this synergy between, here is the structural element, carbon, but here is nitrogen in the right forms, concentration, ratios, times and spaces that give us the actual biochemical process. And so really it's understanding that nitrogen economy that is just as important in understanding plant growth and, in a sense, sustainability. So not just carbon, you know, liquid sunshine, how do we actually sort of basically get that as structure, but how do we actually manage nitrogen in the biochemical process? And of course, as part of that biochemical process, how do we actually get the mineral cofactors for the enzymes, which are effectively essential for that biochemistry? Things like magnesium, which of course then is needed for photosynthesis in chloroplasts to drive that. And of course, we've got to understand the whole lot is governed, of course, by water, because all these biochemical processes, all this life depends fundamentally on water. And of course, all these processes are driven in a aqueous biochemical medium. So really, we've got carbon, nitrogen, minerals, and water as the essential building blocks for life on land, plant growth, and of course, we've got to understand how this all works. And the message is it's actually nitrogen in the right forms, quantities, place, and time that is really the actual catalytic driver of these life processes. And so the availability of nitrogen is critically important. And so the issue is, have we got the right nitrogen at the right concentration in the right place at the right time to give you that optimum efficiency? So it's a very dynamic process, but also it's very, very important to understand nitrogen is a very powerful reactive biochemical molecule. So if there's too little, if we're starved of nitrogen, obviously we don't have growth, right? No matter how much carbon, water, minerals, we don't have the nitrogen, we don't get growth. So it's growth limiting in a big, big way. But most concerning is that if we have excessive nitrogen, then we are also in a dangerous toxicity situation where basically we can have overactivities, hormone imbalances, but also excessive oxidation of carbon. So excessive nitrogen can actually deactivate and destroy the actual carbon structure that we're trying to rebuild through plants. So it's a bit like a drug, you see, it's got to be the right amount at the right time. Too little, dangerous or counterproductive. Too much becomes positively dangerous. And the key thing that then comes into what regulates the quality and the availability of nitrogen in these systems is really the key point. And of course, all of the processes that govern nitrogen availability are driven by microbes, right? Driven microbially. And that's the really important thing to recognize, that it's actually the healthy soils, the actual microbial ecology in those healthy soils, which govern, in a sense, the availability of nitrogen, its adequacy of supply. And it follows that rebuilding healthy soils with these natural nitrogen fixing dynamics processes is really then our point of agency, the key basis through which we can rebuild productivity. And of course, that's where the whole biostimulation of microbial ecology is so important, right? We don't tend to look at that, particularly in the last 100 years. We've always seen nitrogen as, oh, can we just add fertilizer? But in nature, it's actually the microbial activity dynamics that govern the availability of nitrogen and give you that sweet spot of optimum growth. And it's actually a very simple natural processes that, in a sense, drives that whole availability of nitrogen. And it starts off, as with all life on Earth, it simply starts off with photosynthesis, carbon fixation. And of course, as we know, there's CO2 fixation through green plants. And basically, as we fix carbon, then we've got sugars. And then obviously, it's a question of how many of those sugars are either oxidized back to CO2, but how many of them are alternatively converted into stable soil carbon, to humates and glomalin. And the fraction of carbon that can be turned into these stable soil carbon humates, they have got a unique property because they've got vast numbers of negative charges on their surfaces, right? So you can think of this as, in a sense, Velcro almost, right? That basically, as we form these stable carbon compounds in soils through photosynthesis, through humate formation, we're producing vast quantities of negative charges or Velcro hooks on those materials. And the proportion is just enormous. I mean, if you look at the ratio of negative charges, just say for a sand, a clay, and organic matter, it's in the ratio of 300 to 30,000. So, you know, like the organic matter has so many more negative charges on it. And this is critical from a nitrogen economy because basically, yes, biology fixes nitrogen from the air, but it's how it's then stored and made available that's important. And of course, that nitrogen naturally is stored as ammonium ions, NH4 plus ions. And of course, they then adsorb loosely onto these negative charges on the organic matter. And so we've got this wonderful natural synergy in a sense, as we build soil carbon, as we build soil organic matter levels naturally, we automatically build negative charges, and these negative charges can hold vast quantities of ammonium ions on them and make that ammonium ion available as nitrogen. So you'll see as soils progressively are improved through organic farming, natural farming practices, then the nitrogen availability, the nitrogen content of those soils increases because more and more of these negative charges are actually holding ammonium ions. These ammonium ions, of course, have been converted by microbes from effectively the air. Okay, 78% of the atmosphere, of course, is nitrogen, a gas, but that's two nitrogen molecules with a triple bond held very, very strongly, extremely stable. And of course, in nature, basically, it always remained at that very stable gas, unless you had lightning or some very enormous energy input, but the amount of nitrogen that fixed or available nitrogen it produced was pretty minimal. But what the microbes were able to do was to say, look, I can take nitrogen gas, I can use biochemical energy, and I can convert that nitrogen gas into ammonium ions, and of course, park those ammonium ions on these negative charges. And see, that was happening right from the last 3.5 billion years of evolution, initially as the blue-green algae in water and in soil started fixing nitrogen, making ammonium ions available, storing them, ever increasing the productivity of those substrates. The same thing happens, of course, in the rhizosphere of living plants, where there are asymbiotic nitrogen-fixing organisms, things like Azotobacter, Azospirillum, and these organisms are taking sugars from the rhizosphere and again, just fixing atmospheric nitrogen, making ammonium ions, parking those onto the negative charges to make it available. And of course, we've also got, of course, the legumes or the nitrogen-fixing symbiotic plants that are in fact just basically converting the same atmospheric nitrogen into nitrate, but in this case, in the context of nodules. So we've got basically blue-green algae, free-living asymbiotic nitrogen-fixing organisms, bacteria in the soil. And then we've got these legumes. We know a lot of the legumes with the rhizobia, but there's also lots of other associations. For example, casuarina has an actinomycete franchii that again is fixing prodigious quantities of nitrogen every year through these nodules, through the franchii actinomycetes in their nodules. So basically nature has got this enormous factory of microbes taking gaseous nitrogen, converting it into ammonium ions, and where there is good soil organic matter, and as good soil organic matter and soil carbon is improving, able to park those ammonium ions onto those negative charges to make that nitrogen available naturally in the soil. And in a healthy natural system, there's more than enough natural nitrogen in the soil on these charged surfaces to sustain the productivity of those plant systems. most biosystems need some 20 to 40 kilograms of nitrogen per hectare per annum to drive their biochemical processes. And mostly there's enough of that in healthy natural soils. Where there's shortages, then basically nature has exquisite ways of speeding up the cycling of that nitrogen. So then obviously as more nitrogen is demanded, for example, in more productive rainforests, you'll find that the cycle, the speed at which that nitrogen is being used and recycled and made available again and again and again increases. And so again, because of this storage of ammonium ions on surfaces, plus the cycling, natural systems rarely run out of nitrogen as a limiting plant productivity factor. So in a sense, that's how nitrogen functions in nature, right? It's basically driven by microbial ecologies, the active, healthy growth of these organisms in the soil, and basically the capacity of the organic surfaces, the charges to absorb, store, and make them available. And then as things get more productive, the enhanced cycling of that nitrogen through those biosystems. So even if there's only 50 units of nitrogen in that biosystem, it's being cycled more and more actively. And of course, that cycling, as we all know in agriculture, is really very, very much enhanced by herbivores, for example, where you've got people graze or herbivores grazing biomass, basically fixing again that biomass in their guts, fixing more nitrogen in their guts, and then excreting high nitrogen urine and excreta to drive ever more productive systems. And of course, it's not just cattle, it's not just big herbivores, it's all the insects, it's all the termites, all the organisms that are actually involved with cycling this nutrient, driving and enhancing the nutrient cycle. And so in nature, we end up with this really beautiful sweet spot of adequate nitrogen, a carbon-nitrogen ratio in those sorts of biosystems of some 20 to 30 to 1, right? 30 molecules of carbon to 1 unit of nitrogen. And that's sort of optimizing availability, optimizing cycling, optimizing the whole bioproductivity of natural biosystems. And in a sense, that's what we evolved with. That's in a sense the basis of agriculture. And up to basically the turn of the 20th century, we really were dependent on these natural nitrogen fixation processes, availability, carbon supply, organic matter supply things, and cycling to drive the productivity of our agro ecosystems. We were able to harvest some guano and some, bird droppings and what have you from different areas to supplement nitrogen input and stimulate plant growth. But basically, the productivity of the planet was really driven by these natural processes. And of course, it was very, very productive, very, very biodiverse and healthy, and sustained all the people quite comfortably. Okay, so that's in a sense the natural nitrogen cycle, how it basically forms, and also what it enabled, like really a highly productive terrestrial biosystem across the basically 14 billion hectares of ice-free land on this planet, and really created and enabled the creation of the biosystem we evolved in, and of course totally depended on. But basically, in the turn of the last century, about 1908, we changed all this, because basically we, through the Haber-Bosch process for making munitions for war, developed a new process where we could use immense quantities of energy and pressure, and we could actually convert nitrogen gas directly into nitrate fertilizer, or nitrogen ions. And so we were able to basically do what nature had been doing through microbes, but this time we were able to do it physically. And we weren't producing ammonium ions, but we were producing nitrate, NO3 minus. And that Haber-Bosch process, in a sense, then enabled us to use that nitrate as a nitrogen fertilizer for plants. And there's no question that that basically was enabled, stimulated plant growth, because now instead of nitrogen being limited to that 30:1 carbon nitrogen ratio and having been limited in supply, we were able to produce more and more of it, add it to the plants, and of course stimulate that plant growth. It's very important because basically that extra nitrogen that we were able to form through nitrate was then able to sort of basically, because it changed the hormonal relationship in plants, gave more auxin, more shoot growth stimuli relative to root growth, it was able to grow bigger plants, greener plants faster. And of course, we like that in agriculture, so we started just pouring on and getting yield increases through nitrogen addition because, okay, we had greener, more shoot-dominated plants. And of course, that then has driven actually this whole explosion of nitrogen, nitrate demand in agriculture to grow more and more bigger plants. It's had, of course, enormous impacts. Both, yes, we're getting higher yields of plant in terms of weight, but most of that weight was in fact softer, watery plants. Plants, shoots able to contain more water, often with less root. But also, basically, we then had plants that often had much, much more softer, more disease susceptibility, in the sense they lost a lot of that carbon and a lot of that disease resistance. So we had both higher yields, but also more vulnerable, softer plants, whether it was disease, stress, insect, frost, or whatever. We grew much more softer plants. The addition of a lot of nitrate to our system, but also had some other pretty serious deleterious effects, which we knew of, but we didn't really take seriously in a big way, because basically that extra nitrogen that we were now adding as fertilizer was able to, when it was in excess of the needs, was able to oxidize the carbon that had been built up as part of the nitrogen cycle. It was able to oxidize the stable soil carbon. So more and more of the soil organic matter that we had formed and that had held these ammonia ions and provided natural nitrogen were now being oxidized back to CO2 because of the excessive nitrate. And of course, in a way, we were losing the natural ammonia nitrogen bank in our soils because, yeah, we were oxidizing the carbon, which was actually the storage vehicle to make ammonia available. So while we were adding more and more nitrate fertilizer, we were in fact compromising the capacity of those soils to hold nitrogen in the ammonia form. And so that made those soils ever more dependent on ever more nitrate additions to keep them productive. So we were on that slippery slope of basically becoming moron dependent, ever more nitrogen adding dependent. We also had the problem, of course, with the loss of that soil carbon, then we lost the structure, physical structure in the soil, because the carbon was critical in creating the sponge, the three-dimensional carbon matrix in the soil. And of course, as we destructed the sponge, then the water holding capacity, the aeration, the nutrient surface availability, the rootability, all those soil functions degraded and the soils became more compacted and less fertile. So we had this paradox. Yes, we had this nitrogen nitrate fertilizer fix, but in adding it more and more, we were actually degrading the soils and lowering productivity. So, you know, like what we thought we were gaining in higher yield through more susceptible plants, we were also losing in terms of natural nitrogen economies, natural fixation cycling, and soil structure. And so we've been in this business now for 100 years, okay, where cropping systems, intensive agriculture that we practice over 1.5 billion hectares of, you know, croplands across this planet have become very, very dependent on nitrate additions, right? And at the same time, we are actually mining and degrading those soils to the extent that those soils over that 1.5 billion hectares of cropping land have now lost more than half of their soil carbon and a lot of their biofertility and natural nitrogen supply capacity. So this is becoming a very serious problem because, you know, we are actually, mining, oxidizing, degrading the soil through the addition of this nitrogen fertilizer. At the moment, we're adding about 270% of natural nitrogen basically supply needs into our agriculture. So let me explain. We've basically got what was their nature, 100% of nitrogen supply through the organic matter ammonia ion strategy. But on top of that, we've now added 170% by volume of nitrate fertilizer, and that's now totaling 270%. And so our agro ecosystems are running on 270%. So they're really running on hyperactivity, hyperoxidation, and of course, we've seen that enormous rapid spike in CO2 levels in the air, partly significantly from the oxidation of soil carbon, but of course, in recent decades also from increased fossil fuel use. Okay, so this is very, very serious because it's basically with that 270% of natural nitrogen input into our agroecology, we are actually just stripping their long-term viability, long-term productivity, long-term survival. We've got other problems though, because by adding too much nitrate, we're also encouraging actually the volatilization and breakdown or denitrification of that nitrate fertilizer. It doesn't just stay there. Of the nitrogen that we add, if it's in excess, then obviously most of it, because it's water soluble, most of it leaches and then ends up in our rivers and streams and oceans. And of course is eutrophying those oceans, often contributing to toxic dead zones in those oceans. But also there's a whole series of other bacteria that start functioning, which are actually now turning that nitrate, that excess nitrate, into nitrous oxide, of course, which is a greenhouse gas, and then further bacterial action that will turn that nitrous oxide back into just nitrogen in the air, you know, N2. And so this denitrification process is happening. So we're adding to 70% of nitrogen in our industrial agricultural systems, but basically we're losing a lot of it through leaching, and we're losing a lot of it through volatilization, denitrification, and of course at the same time we're destroying a lot of the soil, stable soil carbon. And we've been doing that for 100 years now, and so it's starting to get really, really serious. And in a sense, we're getting to a situation now where we're completely hooked, dependent on nitrogen, adding more and more nitrogen because we've killed these natural systems. But of course, now we've got energy shocks, we've got other crises, climate extremes, and now we're saying, hang on a minute, we've got to keep on adding more nitrate to sustain or try to sustain yields. Well, we won't be able to do it for long, but we're adding more and more to get less and less return, but we're paying more and more for that nitrogen input. And it's very quickly going to become non-viable. I mean, the whole system is non-viable, but we won't be able to subsidize, we won't be able to sort of, you know, afford to put it in, and we won't be able to afford the soil capital degradation as a result. So the challenge is, can we go back? Can we go back to really what nature had given us? Can we go back to actually regenerating our soils, rebuilding these natural microbial nitrogen fixing processes in those soils, rebuilding the carbon structures, the vast numbers of negative charged ions on those organic matter surfaces that can hold the ammonium ion and make nitrogen available as had previously been done in nature from these charged surfaces? And the answer is, of course, yes, we can. And of course, this is, in a sense, one of the key imperatives and challenges and opportunities for regenerative agriculture, right? How do we now go back from, in a sense, not totally cold turkey? We're not saying that we don't use nitrogen fertilizers, but we use far, far lower quantities more wisely, and at the same time rebuild those natural nitrogen fixation, storage, availability processes. And in a sense, that's the opportunity and challenge, but also imperative, because within the next decade, I think I think the reality, the evidence is that most high intensity cropping systems, most of these high intensity hydroponic systems dependent on these high inputs aren't going to be sustainable, right? Certainly not soil-based systems. And so we're really going to say, look, how do we go back to regenerating and rebuilding these natural nitrogen sources, processes, storage buffers, availabilities, productivities, and resilience? And in the process, of course, rebuilding soil capital, sequestering carbon, putting it back into the soil, in the process, rebuilding more vigorous, healthier, resilient, stable plants with much, much lower susceptibility to frost, wind, insect, disease stresses, because we're no longer going to be dependent on these, auxin hormonally induced, soft, watery, nitrate fertilized plants. So that becomes really the major challenge for industrial agriculture going forward. Can it more or less get off this drug that it's been on, this excessive nitrate drug? Can it wean itself off that, use it much, much more intelligently, wisely? Basically, we should be able to sustain higher productivity, regenerate soils with perhaps 10% of the artificial nitrate input that we're using at the moment. Okay, so instead of running it at 270%, can we run it at 150%, for example? Can we run it at 10% excess, but do that additional nitrogen so it doesn't do the harm, that it's not in excess? And if we can do that, we have an enormous opportunity to rebuild healthy, regenerative agricultural ecosystems. But to do that, as in nature, we've got to go back to the first principles that we started talking about, isn't it? We have to go back to say, right, here are the microbes, whether it's the blue-green algae, the asymbiotic rhizosphere, nitrogen-fixing organisms, the legumes, the casuarinas. Here are the natural organisms taking nitrogen from the air, converting them naturally into available nitrogen. Here are all the herbivores, all the guts of all the herbivores, which again, converting nitrogen gas and organic nitrogen into available forms as urine excreta, be they cattle, be they insects, be they termites, be they whatever. And can we build those nitrogen cycles in our agro ecosystems, both fixing nitrogen, cycling nitrogen, storing and making available nitrogen through increased negative charges on these organic surfaces, and rebuild a healthy biosystem? The answer is, of course, yes, we can. And now the challenge is, like going sector by sector and saying, right, okay, how do we turn this industry that we're looking at and turn that back into a much more resilient, productive, and balanced nitrogen economy. Now, we can talk about some of this in the Q&A, and of course, it's really has to be site specific, but for example, rice production, right? I mean, rice production was able to supply all its nitrogen needs from the blue-green algae and the azolla and the nitrogen fixing systems in that aquatic environment that it grew in. And so basically, yeah, we can re-establish those processes. And here's a process of growing, again, highly productive, highly nitrogen nutritious grains through these natural processes. Similar in dryland cropping, we've got very innovative farmers all across Australia and globally. They're rebuilding their soil organic matter through regenerative agricultural processes. They're rebuilding these soil microbial processes, fixing nitrogen. They're rebuilding the ammonium ion storage in that soil. So they're finding that basically, yeah, their crop can get the 30 kilograms of nitrogen needed to establish, to grow, to be highly productive from these natural sources with minimal requirement for nitrate inputs. Okay, so we've got these people developing cropping systems, and then when they integrate those cropping systems with grazing, stubble grazing, for example, then they're enhancing it even further, because then the grazing animals are cycling all that nitrogen ever and ever faster. So we're ending up with very productive grain production, dryland grain production systems, again, with minimal nitrogen additions. We've got a lot of agroforestry, shelterwood type of ecologies that we're being looking at as well, where again, we have nitrogen fixing trees, you know, casuarinas, acacias. We've got massive biodiversity encouragement, insect herbivores, etc. And again, in this way, we're creating new agro ecosystems where we're fixing nitrogen, we're cycling nitrogen, we're storing and making nitrogen available, and building a very productive agroforestry, orchard sort of ecology, again, with minimal nitrogen fertilizer, nitrogen nitrate additional requirement. So there's enormous opportunities. There's also opportunities, for example, in some of these high industrial systems, for example, the sugar industry, right, which is traditionally used massive quantities of nitrogen, you know, 300 units sometimes per hectare to grow things. Well, of that 300 units, over 90% would normally be lost either through leaching or volatilization or unavailability or occlusion. So rather than adding 300 units and being able to use 20 of them effectively in the plant and losing, you know, 280, we can basically say, can we regrow sugarcane sustainably on 20 to 30 units of input, because we're rebuilding these natural processes and cycling processes. And so there's enormous opportunities for doing this. This is going to become really critically globally. Classic case, and it's really quite a tragedy, is that, for example, civilizations like China, they had been able to sustain over 500 million people for thousands of years, for 5,000 years, and largely because their nitrogen economy had been managed through constant recycling of high nitrogen organic waste onto their agricultural land. And they were demonstrating that, yes, they could sustain highly productive biosystems, high populations through this sustainable, stable nitrogen economy. But about 40 years ago, basically, China too said, hey, we want to increase yields. We want to go into high input industrial agriculture. And they started putting on vast quantities of nitrate onto their cropping soils, often at, again, like sugarcane, extreme levels, 300 units, for example, per hectare. And basically in that process have done enormous damage to the structure and the carbon content of their soil, to the extent that most of those soils have basically been oxidized and degraded to really now be impervious, concrete, puggy soils. And as a consequence, for example, now China is basically no longer grain food secure. It's import dependent. Over half of its actually grain needs, both for human consumption and for stock feed, is now brought in from nitrate farmed pastures elsewhere. But basically, we've got a society which is now completely vulnerable, dependent on these artificial nitrogen fertilized grain supplies, which can't be sustained in their own, whether it's ecologically or even economically or politically. So really, we've got fundamental issues of how do we get back to rebuilding stable, resilient, sustainable nitrogen economies in our soils, because that's going to be so important to our future food production and ecological stability. There's a lot more basically we can talk about in terms of nitrogen, because in a sense, nitrogen and carbon are the two essential building blocks of terrestrial ecosystems. As we said in the beginning, carbon is the actual structure, nitrogen is effectively the biochemical engine for plant growth and therefore the whole biosystem futures. And again, we've done enormous damage to what had been that ecological biosystem balance, where 20 to 31 carbon nitrogen ratio in natural healthy systems. And we've turned a lot of our biosystems where basically now they have carbon ratios of 100 to 1, which means that basically they are no longer functioning. They're just basically storing carbon, but not cycling, not breaking down, and in that way accumulating effectively fuel, accumulating carbon. And so a lot of, for example, the wildfires that we're experiencing and will intensify dangerously across the planet in the next decades are driven by biosystems that no longer have enough nitrogen in them because we've destroyed the natural nitrogen. They're accumulating so much fuel, so much carbon fuel, that they end up with infernos, and in the infernos turn back effectively to deserts. So where we, really destroyed biosystems completely. So we've done a lot of damage there, but also we've done it in the converse, other areas where we're polluting environments with nitrogen effluents. So we've got carbon and nitrogen ratios of 2 to 1, 3 to 1, 5 to 1, but these are such high nitrogen toxic environments where you end up with lots of eutrophication, disease risks, and what have you. So look, we've got to restore this whole carbon nitrogen balance. We can do that through rebuilding these natural nitrogen cycles. We can grow crops. We can meet our future food need for the 10 billion people that we project by 2050. But basically, we have to look at nitrogen in this role and then say, what does regenerative farming, what does soil microbial ecology, what does rebuilding soil carbon, and what does then stimulating that microbial biology of that soil, what role can they play, and how do we apply that locally in different ways? So look, I'd like to perhaps stop there, and then let's open up for questions, because I'm sure some of these points we can cover in more detail in the questions specifically.
Fantastic.
Okay.
Thanks for that. Yeah, thanks for that, Walter. So I'll go through the questions for you. We've got a few in the Q&A box. I think this is one that people are going to have to probably watch a couple of times to get all that information that you've passed on to us.
Yeah, yep, I appreciate, yeah.
So first one's from Rob Hetherington. Yeah, he says he's going to get in early on this one because he sometimes puts his things in late and misses out. But he understands the minerals like cobalt, nickel, moly, and the CalMag and all that's all important. But his question really is how do we keep the nitrogen cycle going in the winter months when things cool down and the biology slows down?
Okay, well, look, yeah, no, okay, good. Obviously, yes, I mean, because we are dependent on microbial ecologies for all these processes, right? Then obviously microbes are governed by their own environment conditions. So in winter, yes, there's slower microbial activity. It's a question of how much storage. I mean, if there's been lots of nitrogen that have been stored during the warmer months onto the organic matter surfaces, then that shouldn't be not available, right? Certainly, it's a question of how much buffering you've created in that soil to supply the nitrogen you need, even over the winter months. I think there's another reality, though, is that, yes, things are going to grow as in nature a bit slower in winter. And so if we've been dependent on saying, look, we need winter crops to maximize, then, yeah, that's something we may not be able to do quite to our expectations because, as I said, these nitrogen microbial processes are a bit slower in the winter. So I think it's, again, for Rob, I think it's a case of looking at what the crop you are growing, where you're growing it. It's a little bit of case too of, okay, how much, what is the environmental exposure of that agro ecosystem at the moment? Can you basically buffer that? Is it a cropping thing, or have you got a perennial system? So there's a lot of variables that we might be able to sort of modify to say, yep, let's keep nitrogen economies going. But definitely you're right, they're going to be slower over the cooler period. Now the question is it sort of like running at 20% of optimum, or is it running at 60% of optimum, right? And if we can keep it at 60%, that's probably about what we could hope for.
Yeah, fantastic. So next one's from Simon. Walter, please, can you touch on the damage to the water cycle from use of nitrate fertilizers?
Okay, well, look, yeah, there's no question at all. Like nitrate fertilizer, because they're negatively charged, basically they're not absorbed onto these organic matter surfaces. They're basically soluble in the soil solution. And so nitrate is available effectively, yeah, hydroponically in the soil solution. And then if there's excess rain, it will leach out. And of course, it will go into the rivers and of course into the lakes and then the ocean. And so there's enormous damage, because once we have excessive nitrate in our waterways, then we can encourage a whole lot of other problems, blue-green algae. And so, for example, the eutrophication, because then the algae, the bacteria growth in that waterway will take so much oxygen that will sort of take out the oxygen that other organisms need, and we can often basically kill that waterway or the life in that waterway, right? In the case of sugarcane, for example, that then leaches out onto the Great Barrier Reef, and now we have this perfect nitrogen soup. And that can be extremely beneficial in, for example, allowing crown of thorns embryos to develop. And so we end up with population explosions of pests, for example, in the Great Barrier Reef. So then there's a whole lot of, sort of disruptive ecological disturbances that can flow from that. But the main thing is we are basically losing the nitrogen we're putting on. We are in the process oxidizing. It's fair to say that every gram of excess nitrogen to its biological use in a soil will be oxidizing some 30 grams of carbon from that soil, because that's just the biochemical accelerated compost breakdown process we induce. So effectively, you see, by having excess nitrate in an agro system, we are losing 30 grams of carbon per gram of excess nitrate. And that over time is absolutely destructive to then water holding capacity, root growth, infiltration, productivity, you name it. So yeah, we are destroying agro ecosystems through both that nitrate, the direct leaching, but also its carbon breakdown, soil carbon breakdown effects.
Yeah, no worries. So yeah, at the end of the day, it destroys our structure, it gets rid of our carbon, and so we just can't hold that water or cycle it. So important that we really understand that.
Yeah.
So Walter,
I think another point that isn't recognized often is, you see, excess nitrogen acts like a hormone, giving extra oxygen to the plant, so you get much more shoot growth rather than root growth.
Yeah.
Whereas in nature, you might have a root-shoot ratio of 1:1. Once you've got a hydroponic plant in a high nitrate environment, you've got a root-shoot ratio of 1:10. So you've only got 10% of the root system. So
yeah.
basically, your chances of getting any other nutrients and mineral uptake and drought resilience, anything, you're down to, well, you've got 10% of the roots, you've probably got 5% of the capacity to survive. So again, it's imposing this enormous stress vulnerability factor onto those softer plants.
Yeah. No, very good. So Nicola Maddock, good question here for you, Walter. Could you please explain why we cannot see all the available nitrogen to a plant on a soil test? And how can we see if we have nitrogen in the amino acid form?
Okay. Okay, right. Look, thank you very much. Complicated question because it depends what tests, when, under what circumstances. But as we explained, you see, basically, we've got microbes fixing this nitrogen and then parking a lot of it on these negative charges on the organic matter. But there's also a lot of nitrogen locked up in the biomass of the actual microbes in the soil. Think of it, there's more weight of living microbial biomass in a square meter of soil than there is vegetation above it, weight-wise, right? So, and all that biomass is very highly nitrogen. And so really it depends what your soil test chemistry reaction mechanism is. Are they looking at total nitrogen where they've destroyed and looked at all the proteins, amino acids, you know, microbial content, or are they just looking at what can be leached off surface negative charges as ammonia mines, right? So yeah, tests will measure different things. Tests are valid, but only in a comparative sense. If you're saying, look, I've got soil A, soil B next to each other with different treatment, I've used the same test, I have 50% more availability here than there. But no, it's a very complex thing to sort of say, look, here, have I got a total nitrogen measure? Because it depends what the chemistry and how resilient that nitrogen was, right?
Yeah. Yeah, no worries. So Ken's question is, what role do you see cover cropping playing in achieving the rebuild of carbon in the nitrogen system?
Okay, well, thank you very much. This is part of the regenerative story now, and of course, very, very important, right? Because if you can go 365 days, you know, continual cover, green cover cropping, you're forever putting more carbon into that soil through sugars, root exudates, etc., right? Roots. And so you're adding always more to that stable carbon pool that is able to hold the ammonia mines and therefore progressively build up. But all the microbial activity of these organisms living. Okay, so the conversion from the atmosphere into nitrogen fixing, as we said, it's a blue-green algae, the asymbiotic nitrogen fixers, rhizobia, and of course then the insects and what have you. And the more you can stimulate, and the longer you can keep that stimulated, the more net flux of nitrogen you've got from the air back into your biosystem. And this is of course where biostimulants can be enormously helpful, because it's basically cover cropping, mixed cover cropping, 365 days green, active plant growth, and then basically you're actually fixing nitrogen all the time. It comes back partly to the first question, isn't it? Like, how do you keep nitrogen going even in winter? Well, if you've got a multi-species cover crop, you'll find that, yes, some species are more winter dominant, other species are summer dominant, but if they're all still growing and pumping out exudates, fixing nitrogen through these microbes, then in a sense, you've got a system that's highly buffered and continuous.
Yeah, and Luke, we had a question here in the chat room from Carol Lim about that, asking, will cover crops help fix the nitrogen in winter? And that basically you've just answered that as well. The answer to that is yes,
Yeah.
absolutely.
Perfect. And of course, this is often where the beautiful synergies happen, isn't it? Because there's your cooler legumes, basically over winter, and they're recharging those nitrogen pools, the organic nitrogen pools. So next spring, when you've basically got the exploitative, opportunistic grass growth, the grain cropping, yep, it's got nitrogen for the first 8 weeks of its, growth and seed filling, to give you then the 2 tons of grain yield that you're going to get from that pooled nitrogen or stored nitrogen pool.
Yeah.
Yeah. How are we going for time, Darren?
Oh, good, mate. We're at 10:32, so still got sort of 20 minutes we can probably keep going for, no problem.
Yeah, no worries. So another question here from Nicola Maddock. So do you think the hormone imbalance in the plants transfer to humans, maybe resulting in hormone imbalances and autoimmune diseases?
Okay, Nicola, yes, thank you very much. And of course, we are what we eat. And so obviously the eating healthy, natural food that has been grown naturally is beneficial. Generally speaking, it's a question of how much of what food grown what way are you eating of our diet. It's not likely that we're going to say, yes, because we fertilize this one plant, we're going to get excess hormones, and that's going to affect our biochemistry in a major way directly. But I'm sure there are, if people on an exclusive diet, in some ways, I'm sure those situations can arise. Coming back to the bigger picture, of course, the soft, watery, hormone-induced plants with artificial fertilizers now contain often less than a third of the essential nutrients that natural plants do because of the compromised root-shoot ratios, compromised nutrient uptake. And so, like we might be eating a lot of this hydroponic stuff, but its food value, its nutritional value, maybe 10, 20% of what we assume it is, because the same species grown naturally has a completely different nutrient balance and concentration. But look, it's yes, it affects the hormone balance of the plants. And then I suppose we've got this question, how does it affect our human physiology? Well, it depends a lot on what combination of foods you're eating, but it will have a minor transfer effect, yes.
Yeah, I think that could be a whole webinar all on its own, our agricultural system.
Yeah, that's very important. But
nutrition.
Yes, I agree.
Yeah, so Jackie Thyme has got one here. She's in a bush environment, eucalyptus dominant forest, has a thin layer of leaves and barks on the ground, but nothing's breaking down. Is that a C to N ratio too high, too low? And how can she fix that issue?
And Walter, this is a good one for us. We've done a bit of work down with eucalypts down in Tasmania. We've been on a couple of tours down there.
Yeah, no, look, totally agree. And this is actually a classic situation where, yes, of course, we've got a eucalypt forest. And of course, especially if it's in a planted eucalypt forest, not necessarily a naturally colonized, evolved forest, we often then have excessive litter with high phenolic levels, acid leachates, and basically that's killing a lot of the microbes, very little nitrogen in the system. and you end up with carbon nitrogen ratios in that litter, in that forest environment of 100 to 1. Very stagnant nutrient cycling, obviously, litter cycling, nutrient cycling, and of course, with that stagnation, loss of productivity. And of course, in nature, it didn't evolve that way. Nature then always said, look, I've got to bring nitrogen fixing, nitrogen cycling ecosystem organisms into that. But often in those forests, it was the insects, right? So you basically said, look, I've got leaf-eating insects, and they're turning half of the canopy of those eucalypt forests into effectively insect frass, insect excreta. So you've got things like Chrysopsata bimaculata and all these leaf-eating insects really grazing the forest, and then adding nitrogen into the litter to help break down that litter to allow the nutrient cycling in the soil to happen. But yeah, we can disturb that, and we have done. For example,
Hope he comes back.
Yeah.
We've taken eucalypts into California, we've taken eucalypts into Portugal, into India, but we didn't bring the soil microbial ecology that. So again, hello?
Yeah, we got you back.
You there, Walter? You might need to turn your camera off, Walter. Dear. Anyway, I think we can tackle this next one anyway, Darren, with a couple of things. Adam has got here what are some practical tips broad acre croppers can be immediately applying to their systems. Should we be buffering our fertiliser with carbon sources like humates and fulvic acids, etc.? Yeah. So I'd like to have a say on that one. I think, yes, in the short term, that is worthwhile, but in the long term, and also in the short term, the first thing we need to really do is start to rebuild our biological system so we can build our own carbon source down there to buffer, and just move slowly away from those high input fertilizers. Maybe take 20% away the first year and 10% each year after that as you improve your soil life. So, but yeah, definitely at the start, humates and fulvic acids will help.
Yeah, and we
I think Walter's back, is he?
trying to get back.
Hello?
Yeah,
Yep.
we got you back, Walter.
You have to turn on your microphone, Walter.
Right. Can you hear?
Yeah, we got you.
Okay. Right. Sorry. So we were talking about carbon nitrogen ratio, eucalypt forest, and really that's what we did. We took eucalypts to California, India, I think. We didn't take the microbes that broke it down. It's accumulating enormous fuel levels, 8 tons per hectare per annum, no breakdown. And of course, Hollywood burns every 3 years as a consequence. And of course, to avoid it, we've got to change that carbon nitrogen ratio of that litter. We've got to rebuild basically that breakdown of that litter. So the whole story, it's fire or fungi, right? It's a case of unless we break down those organic litters, those fuels, we're going to have wildfires. And again, that's a major, major threat to a lot of biosystems globally now, because a lot of the biosystems, we've grown them as forests for trees, fuel, but basically we're not building that healthy cycling and of course accumulating fuel and then risking wildfires.
Yeah, interesting. So Luke, there's a question here back here from Ken. I don't think we've answered either. He talks about modern day ag, being, an intensive extractive process akin to mining our soils essentially. And he says, what role do you see cover crop playing in achieving this? in restoring our systems? And do you see the sense in applying high levels of N to cover crops as a means to maximise soil carbon storage?
Okay, look, thank you. And it's just a teaser, isn't it?
Yeah.
As we said before, cover cropping, very important. So we've got to maximise plant growth to get root exudates and root biomass and microbial activity, and of course the biostimulants, like very important that they're playing a role in this. If there is nitrogen limitations, in getting those cover crops up, for example, we're very degraded structurally soil, then yeah, can we add a bit of nitrogen to stimulate that biological activity? And yes, that's valid, but it's valid up to basically 10% perhaps of the level, because once we get above 10% and we end up adding more nitrogen than the microbes can use beneficially, we end up being oxidative and destructive, right? So there's no simple, yes, it's so many milligrams per hectare, or, etc. It's a case of reading each situation and saying, yes, how do I stimulate? How do I get best plant growth, but not go into toxic, excessive oxidation?
Yep. So less is more, Walter.
If you're then adding that nitrogen, very, very much say, can I add that nitrogen in a sense already organic sources where you don't have, where it's still ammonia based, okay? So it hasn't got that risk of oxidation and leaching that it does from nitrate.
Yeah.
Yeah. Yeah. So following on from those sources, what about amino acids? Are we better off delivering our nitrogen as an amino acid, or are we better off doing it as a foliar? Those sorts of things. Because if we can do it as a foliar, we're not going to have that excess going through, are we?
Okay, look, no, you're right. And again, this is complicated. You've got to ask for what situation, what are the costs. Now, obviously, yes, if you're adding it at amino acids, well, obviously, plants take up nitrogen either as nitrate or as ammonium ions, not directly. So there you're looking at, you'll have organisms that are breaking down the amino acids to make them available for uptake, right? So in a sense, yes, for plants to get the nitrogen, you do have to go back to those mineral ions. But it may be that, yes, there's a smart way to add nitrogen, because then it's stored as stable amino acids or other, like fecal compounds, and then it'll be broken down and made available as the plant needs, rather than being as vulnerable to leaching. As far as foliar sprays, yes, that can be very beneficial because it allows plants to absorb, for example, the nitrogen directly, so without leaching, etc. But the danger is if it's excessive, or if the capacity isn't there, it could also enhance volatilization, right? So you end up with basically bacteria breaking down whatever you've added as a foliar and going straight back into nitrous oxide or nitrogen itself. So look, it's a question of, yeah, adding sources, and then what are the different bioconversion processes for those sources, and yeah, how do you minimize leakage and maximize effectively for that crop in that situation? As a general rule, it's fair comment to say the more buffering you have there, the more soil organic matter, these negative charge, Velcro, storage mechanisms as a buffer, that's often very, very beneficial right across the spectrum.
Yeah. Another really quick question, Walter, here, which is it might be a hard thing for you to answer or measure, but how much nitrogen in total can natural systems sequester?
Okay. Okay. Well, look, right. This actually, we don't always have the exact answer to that. We do, look, we have done a lot of studies in CSIRO. This is when I was working there, where we're saying, look, yeah, here's the amount of nitrogen that is these systems, for example, rhizosphere nitrogen fixing and legumes can fix. And, you know, like basically 40, 50 kilograms per hectare per annum is, you know, roughly the plateau at which these natural nitrogen systems can actually sequester nitrogen. And that's more than enough to sustain most biosystems. But then we have other really interesting things, isn't it? We have natural biosystems, for example, sugarcane. And sugarcane can grow at 200 tons per hectare per annum above ground and another 150 below ground, right? So it can produce prodigious quantities of biomass. And you've got to ask yourself, well, where is it getting all its nitrogen from? And of course, it's getting its nitrogen from these, rhizosphere nitrogen fixing organisms. But then the question is, right, how much nitrogen is actually being fixed by that sugarcane? How much above that 50 measured threshold might that be? Probably be close to it, right? If you got to say 200 tons, yeah. But so we don't actually always know, because it comes to the question of soil tests. What form is that nitrogen in? And if it's all locked up in plant biomass, we're not going to necessarily measure it in a lot of the other extractive soil analyses, etc. Right? But as a budget, an overall budget factor, about 50 kilograms nitrogen per hectare per annum is a good high level. Hello?
Yeah, you're breaking up there a bit, mate.
Oh, okay.
No, you're back. You're back, Walter. It seems all right again.
Yeah. Okay. Good. Next Next question. Yeah, please.
So, Luke, have you got? Do you want to? There's a couple of questions here that I can probably answer. One from Nakala again, but we've got one here from Roger Sendell. So he asks, what is the difference in planted multi-species cover crops opposed to natural first successional covers in regards to nitrogen building for the following winter crop?
Okay, thank you. Look, okay, basically, it depends on what the crops are, but it's a very sophisticated, important question. Nature, in a sense, goes through these natural successions. And we saw that actually just recently after the wildfires, the 2020 wildfires. And in many, many situations, you got basically acacia, wheat field regeneration happening in a lot of forest, savanna sort of environments. And again, these acacia seeds have been sitting in that soil often for 100 years, dormant. But after that heat effect and the hot fire, and basically nitrogen being so limiting in recolonizing those burned soils, the first competitive species is then a very efficient, fast-growing, deep-rooted nitrogen-fixing plant like acacia, right? And so it makes the point that where you have natural plant successions that are adapted, they're often more efficient at providing those essential nutrients that that site needs at that time, compared to if you say, look, here is a multi-species conventional cover crop. Okay, so those natural successions would tend to, because they're addressing the limiting factors on that site, tend to be better. But on the other hand, they may not be what you want for your economic system, right? I mean, you're not going to necessarily be able to eat that acacia wheat field cover crop. And so you might be saying, okay, yes, I can, but if I'm growing a legume instead, then at least I can graze it. So what I'm getting at is that, yes, nature selectively has these successional pioneer species, and they are deliberately putting this nitrogen back into the system, restarting root growth. But what I'm saying is that it depends on what your economic objective is, because, you don't necessarily want your wheat field under acacia suckers, right?
Yeah.
Yeah. I think too, it doesn't matter what outcome you're looking for. You've got to have a goal in mind when you're going to put a multi-species in and choose your plants accordingly to that. So,
yeah. And then the other thing, when you're putting a multi-species or any crop in, you've got to always ask to say, well, look, how do I recycle the biomass from this crop after? Have I got an animal that eats it, or am I going to green manure it, or whatever, right? How am I going to turn it back into next rotation productivity?
Yeah. Yeah. So, Darren, do you want to tackle the, do you want to answer Nikala's question? Because living in the wonderful country that we live in, people don't think that they can grow a summer cover. So biostimulant is a really handy tool to utilise coming into a winter crop if they haven't had something growing over summer. So do you want to tackle that? And
so yeah, so she's asked how does best biostimulants work, which is interesting. So our signature product, TM Agricultural, has got is made up of so many different ingredients. Some of them are natural biostimulants in their own right, like fish meal, kelp, molasses. So all of those things are in there. But the main ingredients in our product are plant extracts, which are the liquid parts of plants essentially, and it's a wide variety of plants that we extract those liquids out of, which are essentially sugars and carbohydrates. And these sugars and carbohydrates, once sprayed out on the soil, they mimic a biodiverse system, which biology react to. So we're like giving these exudates feeding these exudates to biology, and we are tricking them into thinking it's in a really healthy ecosystem. So they will activate and repopulate and then signal to each other to come alive, and they then form a relationship with the growing root systems of plants, and thus creating the photosynthesis that we've spoken about. So we help really fire the bugs up to get the nutrients from the soil to the plant.
Right. And look, if I could add to that, this is a very important question, but I mean, again, it's no question it's all proven, but it varies from place to place. Obviously, yeah, the biostimulants work by stimulating that soil microbial activity of all these different bugs, right? And basically that's switching on at 10 times a rate organisms and processes that otherwise wouldn't be happening, whether it's nitrogen fixing or whatever. And the plant extracts are, in a sense, part of that stimulation. But I think you have to look back and say, well, what does an organism or microbes in soil need to be happy, to grow, to be active? And obviously they need the right moisture conditions, they need the right oxygen, they need sugars or substrate from, the plant roots. And then they need things like cofactors and buffers. But the cofactors is where these plant extracts come in, you see, and this is where there's successional planting and so forth. That, different cofactors, different plant extracts are then very important at switching on different suites of soil microbes. The other thing is, the buffers, like basically with the, if there's adverse situations in the soil, it's too acid or something like that, then basically this is neutralizing some of these adverse consequences, and that again keeps the soil microbial ecology healthier. So while we don't have, yes, we can look at individual organisms, say this is what's switching as a overall blanket. We are saying, look, these are switches for microbial activity, which enhances this whole suite of organisms. And it's, again, nature will pick out what it needs, and it says, look, I need to get these things going, and these biostimulants help me do that.
Yeah.
Yeah.
Yeah, very good. How are we going, Luke? We got other questions?
Yeah, there's another couple here that we haven't addressed. So Richard Allen has got a question here. Walter talked about the natural system producing yields of 2 tonnes per acre, but how can we still produce yields of 4 tonnes per acre if that is the yield at present? So Yeah, Walter, do you want to have a go at that? I've got something to say about that one as well. So,
Yeah.
Walter, you go first.
No, and I was just using 2 tons as baseline, you know, like sort of hard dry land cropping baseline, right? Now, yes, we have been seduced into getting 4 tons because if we're adding all these requirements, yes, we can get up to 4 tons, right? Obviously, in Europe and stuff, they go up to 12 tons because, hey, they can add more and they've got very much younger fertile soils. See, we always focused on the 2 tons or the 4 tons. Well, the question is, one is how healthy is that growth? How long is it growing for? So there's this variable time. So, you know, if we have a crop doing 2 tons, but it's growing for longer and sustaining and it's got perenniality, then is it getting, you know, over a longer period of time, getting closer to that 4 ton anyway? Another question is what is the actual nutrient content of that grain, that 4 tons vis-a-vis the 2 ton?
Must be dodgy reception in Canberra this week.
Yeah, maybe.
Grain, because if the 2 ton integrity balance compared to the, if it has, I just saw the disruption here. I don't know why. Hello, are you back? Yeah, we're back. Right. Okay, if the basic, good. Okay, so if basically it's got the higher nutrient density, is a 2 ton crop with nutrient integrity equivalent to 3-4 tons. The next question is, you see, we've always looked at maximizing yield per unit of area and per unit of input. But if we're putting in 10% of the input, right, and we've got plenty of area, is basically growing 2 tons over twice the area with less input a smarter strategy in the first place? So do you get what I'm saying? Like, there's always mine is bigger than yours, therefore mine's better. But there's many, many other metrics and questions we have to ask. Well, what are we actually trying to achieve? The last one in that comparison, if I can grow 2 tons, you know, like 8 years out of 10 reliably because I've got a resilient system, is that better than growing 4 tons 3 years out of 10 when the things are optimum, but for 5 years out of 10, I've got nothing because the crop hasn't been able to get established or I've had to put the stock in. Okay, so there's all these factors of integrity, input costs. Is time a limiting factor? Is area a limiting factor?
Profitability?
Yeah, all these other metrics. And in a sense, we've got to rethink agriculture. What are we trying to achieve? And yes, we want net good quality food outcomes, but if we can do it with 10% of inputs over twice the area for a little bit longer, then we're winning in every sense. Yeah, and look, we Best actually did a trial up in northern New South Wales last year, and the results were pretty simple. Like the full-blown let's throw urea at it and a starter at it and all the rest of the thing at it, and the cost was, let's say, $400. I can't remember exactly what that money was. And then we did different stages, and the one that cost the least was the most profitable by a considerable way, like maybe $300 or $400 a hectare more profitable than what the higher yielding one was, and it didn't yield that much lower. It was only a couple of 100 kilos anyway. So, but exactly. that was in a system that has been fixing itself for about 8 years, so 6 or 8 years. So, yeah. Look, and this epitomizes. So we really need to rigorously look at these metrics. What are our performance measures? I don't want to be rude, but really we're facing a very serious thing globally, and it's almost winner take all, right? The issue is who's going to be able to keep on economically functioning, growing reliable crops, 4 years out of 5 rather than 2 years out of 5, able to minimize their cost, have resilience and survive. Because at the end of the day, that's what's the crunch points. Can I survive? And then if I can survive, winner takes all, right? Whereas all the others saying, I could run faster, I could grow bigger, if, but if the ifs aren't there, then you're dead. And if you're dead, you're not productive.
Yeah, absolutely. I think that's, we're about time, aren't we, Darren?
We are, mate. Yeah. If we've got any other questions here, we can have a look at them and answer them direct anyway, and get them to it. So yeah. So I think we're at 11 o'clock. So I guess at this time, Walter, I want to thank you for your knowledge again and sharing that with us, because it's invaluable. I'm seeing a few comments here in the chats about how good it is to hear you talk.
Okay, and thank you, and I appreciate that this nitrogen economy, biochemistry is a complicated subject, lots of detail. We've, in a sense, skated over for 100 years. We haven't looked at it. We've always said, oh, let's just put more on, but it's actually a very, very important thing for the actual future and really agricultural productivity going forward.
Yeah, and we really appreciate everyone listening in, and Luke, again, thanks for being a panelist and supporting what we're doing as well. If you want to have the last say as well.
Yeah, thanks again, Beth, for putting it on. Thanks, Walter, for your knowledge. And for everybody that's listening to this, if you've got questions, don't hesitate to contact us, and we can help you through some changes. That's what we do as a business, and I know Best is always answering questions for people. So don't hesitate to reach out if you want a hand.
Thanks heaps, Walter. Thanks again. And I'm sure we'll have many more in the future. We'll use you again.
Okay. Well, look, thank you. And looking forward to it, and enjoy. Beautiful day. And let's enjoy. Okay.
Thank you very much. See you guys.